Hello and welcome to Lecture 2 of Electromagnetic Induction. In this lecture we're going to look at the idea of magnetic flux, which is basically exactly like electric flux, which we saw earlier in the course with Gauss's law. And then we're going to meet Lenz's law, which I think is one of the most confusing laws in all of physics. So I'm not going to say very much about flux. We covered flux in great gory detail back in the Gauss's law part of the course. So if you're rusty on flux, you should look back at that. But just for a quick recap, when we have a uniform vector field, which I'm just calling V, going through some plane of area A, and that plane is tilted at an angle theta as shown in this diagram, then the flux of this field through that area is just VA cos theta, or you can write it as a dot product of V with an area vector which is perpendicular to the surface and of the same magnitude as the area. That's fine if you have a uniform vector field through a plane, but as soon as you have a non-uniform field or the surface is curved, then you need to integrate and things get more interesting. So a magnetic flux is defined just like any other flux. You take that general definition with a vector V and you just replace that with the magnetic field vector B. And you can think of it sort of as a number of field vectors pointing through the surface. Now remember, that's really infinite, but it's proportional to the area of the surface and it's proportional to the strength of the field. And for a uniform B field through a planar surface, then we just have a nice simple dot product. It's worth taking a moment to look at the units. Unlike electrical flux, magnetic flux does have its own unit. So if you look B times A, that's Tesla meters squared, and that is defined as a WB. That's a Weber. And English speakers will often maul that into Weber or Weber, but it's named after a German guy, and so it's a Weber. And it turns up in all sorts of different forms when you actually calculate. So it'll often turn up, look, a Tesla is a Newton per amp meter, right? And so a Weber will often turn up as a Newton per amp meter times meter squared, right? That is a Newton meter per amp, and a Newton meter is a joule. So joules per amps is how it sometimes turns up in a calculation. And then an amp is a coulomb per second, right? So this is a joule per coulomb per second, and a joule per coulomb is a volt. And so it'll often also come up as a volt second. So I promised that we would explain the directions of the induced currents in a coil when you're inserting or removing a magnet. So now it's time to do that. So here's the coil again, but I've set it up a little differently this time. This time, if you look, you can see a resistor here. So there is a wire with the resistor right here, and then the wire goes up around this way and into the coil and around. And so if current runs counterclockwise this time in the coil, it's going to come out here and it's going to go through the resistor this way. And you can see the leads from this voltmeter now. I've connected a voltmeter across the resistor so that, again, if current flows this way through the resistor, which means it's going counterclockwise in the coil, that is what will show up as a positive voltage here. Now I'm going to do the same thing I did before, putting either end of the magnet in or out with this new setup. And I'm not sure this new setup makes it any clearer what's happening, but I'm about to show you a very similar setup that should make it much clearer. So this will make it clearer. I've got almost the same setup. You can see the resistor here, so here's the wire with the resistor. And I've once again set things up so that if current goes counterclockwise around the coil, then it comes out here and runs through the resistor in this direction. And that's going to be read as positive. But now, instead of a voltmeter, I've set it up with a voltage probe, so we can see the voltage as a function of time. So now with this setup, here's the magnet again, and you can now tell when I put the north end of the magnet in, I get a positive voltage, and when I pull it out, I get a negative, and when I turn it around and put the south end in, I get a negative voltage, and when I pull it out, I get a positive voltage. Let's pick this all apart and see what's going on. So we need to think about magnetic interactions, and so we can think about the magnetic fields due to this magnet, but we can also, because we have currents running around in this coil, think about the magnetic fields that it's producing. So here I'm sticking the north pole of the magnet in. Now the north pole of the magnet has a magnetic field out of it, and so that is pointing into the coil away from us. And as I put it into the coil, because the magnet is getting closer, that B field is getting stronger inside the coil. Well, that generated what we saw as a positive voltage, which meant current this way through the resistor, which meant counterclockwise current in the coil. And if you just do the right-hand rule for that coil, that means that the magnetic field that the coil produced as I stuck this magnet in was out towards us. Let's look at that again in the diagram. So here I am putting the north pole of the magnet into the coil. And the B field due to that north pole of the magnet points down. So there's a B field through the middle of the coil pointing down. And as I bring the magnet closer, then that B field inside the coil due to the magnet increases. And so there's a delta B pointing down. But the current that we observe in the coil is in the indicated direction in the diagram, and it produces what we would call an induced magnetic field, which is up out of the coil. In other words, it's in the opposite direction to this delta B. Here is the moment when I pulled the north pole of the magnet out. And so again, there was a B field in due to the magnet, but it got weaker as I pulled the magnet out, and so there was a delta B in the opposite direction, right? You go from an initial large B field into the coil to a smaller one into the coil, so the delta B is this way. Well, if you look, that resulted in a negative voltage on our voltage probe, which is indicating a current this way through the resistor, which means the current was going clockwise in the coil. And if you do your right-hand rule, that means that the B field due to the coil is that way, in away from us, opposing, again, this delta B. So again, let's see this in the diagram. When you pull the north pole out, then the B field that is pointing down through the coil reduces in magnitude, and so there's a delta B which is up, and the current in the indicated direction produces an induced B field down in this case, so opposite the delta B again. So here is the moment of me putting the south pole in. So with the south pole, the B field points towards it, and so the field inside the coil due to this magnet is out of the screen towards us. And as I put the magnet in, that field gets stronger, and so we get a delta B also out towards us. Now, if you look at the data, we see a negative voltage, which corresponds to a current that way through the resistor, which means clockwise current in the coil, and the right-hand rule tells you then that the B field due to the coil, the induced B field, is into the screen away from us, again opposing the change in the B field. Hopefully this is starting to get familiar now, so once again with the diagram. There is a B field inside the coil due to the magnet, which is now up towards the magnet, because that's what we have from a south pole. And as we insert that south pole into the magnet, that B field is going to get stronger. And the current ends up being in a direction so that it produces an induced B field opposite to that change in the B field due to the magnet. It should come as no surprise then that as I pull the south pole out, we get a positive voltage indicating a current this way through the resistor, which means counterclockwise current in the coil. The right-hand rule tells you that that means an induced B field out. Well, that makes sense because the B field due to the magnet inside the coil was out, but it got weaker as we pulled the magnet out, and so the delta B was in, and so once again the induced B field is opposing the change in the B field. And so this final case, pulling the south pole out, looking at it in the diagram, again, the B field due to the magnet inside the coil is up, but as you pull it out, it gets weaker, and so that means there's a delta B which is down, and the induced B field that we can get from the direction of this current is up, so opposite the delta B. The other really crucial thing to notice is that when I hold the magnet still right next to the coil, there is no current in the coil. So it isn't the magnetic field of the magnet that causes a current in the coil, it's the change of that magnetic field. If I hold the magnet still, I get no induced current. And the other thing is, right at the beginning, as I was showing you the magnet, you can see that each time I rotate the magnet, you see a little bit of current in the coil, because me rotating the magnet is also changing the field inside the coil. Let's compare the situation we just saw where we were changing the B field inside a coil and seeing that it caused an induced current with the situation we saw in the last lecture with a moving rod having a motional EMF and that driving a current. So in this case, the B field is constant. What's changing now is the area enclosed by the loop. This area enclosed by the loop, as the rod moves this way, is increasing. And so that means, although the B field itself isn't changing, the magnetic flux is increasing. So this is a B field into the page. Flux isn't a vector, but let's call into the page a negative flux. So we've got a negative flux that's increasing. Well, look at the current direction. That current direction is going to cause an induced B field out of the page. And so that's causing a positive flux. And so the flux due to this induced B field is opposing the change in the flux resulting from the motion of the rod. So it's not that the current flows to oppose the change in the B field. It's that the current flows to oppose the change in the magnetic flux. So now we're ready to state Lenz's law, and it's a tricky one. It takes practice to use Lenz's law. It's subtle. So it is if and only if the magnetic flux through a closed conducting loop changes, an induced current flows in the loop such that the magnetic field due to the induced current opposes the change in the magnetic flux. Quite a mouthful. So just remember that the magnetic flux is a B dot A, or BA cos theta, and so that means we have several ways to change the flux. We can change the B field, for example, by moving a magnet, which is the source of the B field, inside a coil closer or farther away. So we can change the B. We can also change the A, such as by pulling a rod this way so that the loop gets bigger. But there's another way. We can change theta, so we could have a loop of a constant size in a constant B field, but we now rotate it like so, and now as cos theta changes, the flux changes, and that's going to drive currents in the loop as well. And that turns out to be a really useful way because you can potentially rotate this loop really fast, which means you can make very large rates of change of your magnetic flux this way.